Hey everyone, this is the last video in the 3-video series on confidence intervals. This one is on how to make confidence intervals when your data is qualitative rather than quantitative. The formulas are a little bit different, but the ideas are basically the same. So let's go see what that looks like. So I'm going to go ahead and share out my notes and see what we've got here. Where they at? There we go. All right, so as you can see, we just left off the end of the quantitative section. And so here, we want to do confidence intervals for proportions. Now, interestingly, these are probably the confidence intervals that you are most familiar with, although you may not realize it. So if you watch, if you're into politics, for instance, you'll often see questions like, do you approve of what Joe Biden has done in his first 2 weeks in office or whatever, right? Something like that, right? And so the answer to that question is going to be yes or no, right? So there will be like 62% of people approve and 38% of people disapprove, something like that. That is actually a confidence interval that they're giving you. Like if you look carefully, when they display that on, say, TV or if you're watching on YouTube or whatever, what you'll see is you'll get like 62% approval with a margin of error of 2.5%, right? What that's telling you is the 62% is the sample proportion, and the 2.5% was how far they go on either side to get a 95% confidence interval. They're actually telling you a confidence interval when you see a poll like that. And so we're going to see how to make those. Yeah, that's very common. So here I take a little bit of time to explain that this is actually a binomial question. It meets all the Bernoulli trials. Like, so here's your question: like, do you approve of the president's performance? We're counting number of successes. The people who approve, we're actually counting proportion who approve, but it's basically the same idea. There's only two answers: you approve or disapprove. Each trial has an equal probability of success, and the probability of success is the proportion of people in the population who would say yes, right? And so as long as you are asking the whole population every time, right? Asking one person out of the whole population, you actually get an equal probability of success each time. And if your sample is taken reasonably well, the trials are also independent. If one person approves, that doesn't change the probability that some other person will approve. Now, on a bit of a tangent, so you can ignore this for the next couple minutes if you just want to learn how to make a confidence interval. But from a practical standpoint, this is not actually true, given the way polls are currently taken. In general, most polls, at least by professional polling firms, are done over the phone still. And people's cell phone numbers are not available to be robocalled. And so what you get is you get a lot of phone polling, and people who both have landlines and are willing to answer polls tend to have a lot of things in common, right? They tend to be older, they tend to be not as technologically savvy or focused. And so in modern polling, independence is actually a big problem. Like, this is in a practical sense, it often doesn't exist. So this last one is a very modern polling problem, that just calling people on the phone, calling random phone numbers, is not a random sample anymore, because the people that you get tend to share a lot of characteristics. However, we are going to ignore that. We're just going to assume that polling is perfectly random. And again, this is back what I don't know if you remember this from the very first video again. But the thing I said then was that the biggest problem in modern polling or in modern statistics, is attempting to get a good sample. This is what I mean. It's hard to get a good sample. All right, aside over, let's see how the math works out. So there is a central limit theorem for proportions. It goes like this. So NP So the sample size times the proportion or times the probability of success gives you the expected number of successes. And then n times q is the expected number of failures. Q is the probability of failure. You can think of it as 1 minus p if you want. If the expected number of successes and the expected number of failures are both at least 5, then it is reasonable to approximate the sampling distribution of p prime, just say that's the sample proportion, with a normal distribution. Little p prime is the proportion of successes in the sample. Big P prime is the sampling distribution of little p prime, right? So it's the relationship is very similar to the relationship between x bar and mu. Capital P prime is the name of a distribution, and it is a sampling distribution of these guys, the proportion of successes in each sample. And if we meet this requirement, well, these two requirements, that the number of expected successes and the number of expected failures are both at least 5, then we can say that the sampling distribution of p prime is this. It's normally distributed with a mean of little p, the sample proportion, in a standard deviation of this, the square root of pq over n. This is not a t-distribution, this is a normal distribution, so we're back in normal distribution land. Now, all that being said, we're still doing this. If we are attempting to estimate the population proportion, then we will use the sample proportion as our point estimate. Our critical value, well, we're back to normal distributions, so we're back to the z alpha over 2's again. And for the standard error, well, that's this, square root of pq over n. That's it. Now, we do run into one problem here. P and Q are parameters. P is the population proportion of successes, and Q is the population proportion of failures. So what we end up doing is approximating those with P prime and Q prime, which is to say the sample proportion of successes and the sample proportion of failures. That's pretty much it. So let's see how that works. I suppose I should write out the formula, write out the entire formula at some point. I'm surprised I don't actually have it in here, but let's just write it down. So we are still doing the standard, the point estimate plus or minus critical value times standard error. But now the point estimate is little p prime plus or minus. The critical value is back to z alpha over 2 because these are normal distributions, times the standard error, which is we're going to use this as our estimate of that. And that's what we're going to do. So in general, what you're going to do is find this number first and then put it all into the formula. So let's do that. Okay, so Simone, trying to figure out if employees in various Domino's franchises approve of the job that corporate is doing to market Domino's. In other words, you work here, do you approve of the way we do our marketing? So she takes a poll of 824 employees, and 675 of them approve, and the rest disapprove. So we're going to make a 95% confidence interval. So the first thing we want to do is figure out P prime and Q prime. Well, P prime is the proportion who approve, Q prime is the proportion who don't approve. So let's go write those down. So P prime equals proportion of success, which is x over n. So x here stands for the number of successes in the sample, and n is the sample size. So it's literally just x over n, right? Number of successes divided by the sample size, that's the proportion of successes. Q prime is proportion of failures, which is 1 minus P prime. Right, we've only got two choices, success or failure. In this case, it's approve or disapprove. Let me clean up my Q a little bit. And so it's just 100% minus whatever we got for P prime. So let's find those. So we said this was 675 out of 824. I don't remember the numbers. Let me go back. Yeah, I did remember the numbers. 675 out of 824. Okay. So let's figure out what proportion that is. 675 divided by 824. 0.8192, let's say. So P prime about equal to 0.8192. So Q prime, again, we're going to use our subtract from 1 trick here and make 99910. So 0.1808, 1808. And that's all I need, right? I've got so to put it in my formula, I need P prime, Q prime, N, and Z alpha over 2. Well, we're going to make a 95% confidence interval, so Z alpha over 2 is 1.96. And we said it was 824, so that's all our numbers. Let's go to, apparently you can make a new whiteboard without erasing the old one, which is kind of cool. So I'm going to do 0.8192 plus or minus 1.96 times the square root of 0.8192 times 0.1808 divided by the sample size, 824. And so we're going to jam that in the calculator. And of course, we'll learn the shortcut key in just a minute, but for right now, just going to use the formula. So I'm going to have 0.8192 minus 1.96 times the square root of 0.8192 times 0.1808 divided by the sample size, 24. And this is another one where you can see why you might want to not have to retype this and just be able to make that a plus. All right, so we got 0.797929 up to 0. Let's go 3. For significant figure purposes, I should really only go 3 digits since I was rounding to 4 here. You want to go one less. 0.793 up to 0.845. 793 to 845. About equal to 0. What the heck is with my computer? 793. Oh my gosh, my handwriting. 793 pardon me, my picture's in the way. 0.845. That's so messy. I'm sorry. We'll just, all right, good enough. You get the idea. Okay. So there is my confidence interval. Notice that these are proportions. So this is to say that Simone is 95% confident that between 79.3% and 84.5% of Domino's employees approve of the way that corporate is doing their marketing. Let's jam that into the calculator and see how that goes. So we're going to go to the calculator. Now, this is interesting. You need very little information in your calculator to do this, just X and N. So in other words, just number of successes and number of trials, that's it. Because the calculator will calculate P prime and it will calculate Q prime, and you've already told it what N is, and it knows from the confidence level what to make Z alpha over 2. So when I go do this, all we need are X and N. Do remember that X is not P prime. X is number of successes, not proportion of successes. So this is a 1 proportion Z interval, which is down here. 1 prop Z int is the one we want here. We will eventually use all these other ones too, but for right now, single proportion, and we're making a Z interval. X and N. That's all we want. 675 out of 824. Confidence level 95%. 7929, 8.8454. Notice that those are exactly the same thing we got. So that's it. That's all we're doing for proportion intervals. There really is not very much to it at all. It is almost exactly the same as the way we did the other confidence intervals, right? So we're still doing point estimate plus or minus margin of error, and the margin of error is still critical value times standard error. It's just that those things have different formulas. But it doesn't change from our perspective, what we're doing very much. All right, so let's go back to the notes because there's a couple more things I want to show you, and then we'll wrap this up. So there's still the same question about how big a sample should Simone take, right? If she has a particular precision and confidence level in mind, then we can figure out how big a sample she needs to take. Now, we're gonna do it the same way. We're still just gonna solve for n. Now, here's the thing. Takes a little explaining for why this is the case, but p prime, if you choose p prime is 0.5, that gives you the most conservative estimate. Yeah, I explained a little bit right here. P prime equals 0.5 gives the maximum uncertainty and results in the largest n. So if you are being very conservative, you have no idea what p prime is going to be before you take the sample, then you should just use 0.5 to get the largest feasible sample, the biggest minimum, essentially, the largest minimum sample. If you actually have a pretty good guess as to what p prime is going to be before you take the sample, maybe you've done a poll like this before and you're thinking that's probably about the right range to choose, or you figure you have a good guess as to what p prime is going to be, you might be able to get away with a smaller sample, but the most conservative one is the one with the most uncertainty, which is p prime equals 0.5. If you're interested in why that's the case, I'll show you at some point. Yeah, that's it. But it's beyond the scope of the class why that's the thing that we need. Although it's not a thing that you couldn't understand. Anyway, so that's what we're going to do. We're going to solve for n in the error formula. Where's my whiteboard? Here. All right, so we're going to use the formula E equals z alpha over 2 times the square root of p prime q prime over n. Actually, sorry, that's not actually what we're going to do. We're not going to have those primes there. PQ over n. Right, because you won't know what p prime is before you take your sample, right? And you ask this question before you are taking your sample, to know how big your sample has to be. And so, of course, you wouldn't know what p prime or q prime was by then. It's just, if you have an estimate of what you think p or q is, you can maybe narrow this down a little bit, but we're not going to. We're just going to use p equals 0.5, and since q is 1 minus p, q is also 0.5. Yeah, so let's go ahead and solve for n here. So it's going to be basically the same way we did before. E over z alpha over 2 is the square root of pq over n. Oh, when I say did before, what I mean is a couple of videos back when we did a very similar problem. I'll square both of those. So we had E over z alpha over 2 squared equals pq over n. Flip them both over. Sorry, I almost did that backwards. Z alpha over 2 over E squared is n over pq. And so multiply both sides by pq, I end up with pq times Z alpha over 2 over E. Sorry, I almost did it upside down again. Z alpha over 2 over E. Whoops. Whoa. Equals N. Oh, that's squared. Equals N. So that's your formula right there. So this is what I mean by if you don't know, like, we're going to have to pick numbers for these things, and you don't know what P and Q are. Of course, you're estimating P, so you can't actually know precisely what P is. But if you have a guess as to what you think P might be, you could maybe make this number a little bit smaller. But this number right here, this PQ, will be as large as possible when P and Q are both 0.5. So we end up with 0.5 squared times Z alpha over 2. So for making a 95% confidence interval, 1.96. E is your margin of error. And then we square that and we find out. So let's see what that looks like. Here. 95% confidence interval, so we got Z alpha over 2 is 1.96. Margin of error of 2%, which is to say 0.02. And P and Q are both going to be 0.5. So we're going to get N equals 0.5 times 0.5, so a fourth, times 1.96 over 0.02, quantity squared. So we jam that in the calculator and see what we get. So we're going to have 0.5 squared times 1.9, oops, sorry, I forgot to put parentheses. 1.96 divided by 0.02, quantity squared, 2,401, which is a big number. Right? That is a large number that you need. So 2% and a 95% confidence interval is actually pretty hard to get. Like it takes a large sample to do that. In general, if you look at, say, national polls, for instance, that have a margin of error, it's usually 2.5% or 3%. And if you are okay with that, that usually means that, so like a 2.5% margin of error, well, let's see what that would be. 0.5 squared times 1 point, I forgot the parentheses again, gosh darn it, 1.96 divided by 0.025 squared. 1,500 people. That's how big your sample needs to be to make that happen for a 2.5% margin of error. If you don't think it's going to be 0.5, right? If you think it's going to be 60-40, you can get away with a slightly smaller number, right? 0.5 squared is 0.25. If you think that the split is going to be 60-40, that's 0.24, which gives you a slightly smaller number here, which says slightly smaller sample size. 3% is also a really common margin of error. So if I do 0.5 squared times 1.96 divided by 0.03 squared, you'll see this, 1,067. And if you look at the sample size on polls with a margin of error of 3%, it is almost always right around this, 1,060. 1,060 is actually a really common number, so it's 1,069 is a really common sample size. And this is why. It's because that's how you get a 3% margin of error. So if you're ever wondering, why this very specific sample size, because it's never like 1,000 even, right? It's always like 1,068 people or something like that. You might think to yourself, well, why did they choose that specific number? It's because that specific number gets them a 3% margin of error. That's why. Anyway, that is basically all I wanted to say about calculating proportions. Actually, let me go back to the notes for 1 second, just make sure that's it. Oh, I guess we got a little bit of calculator practice here. And then this bit on the Wilson score adjustment, which I'll briefly explain. There'll be a extra credit question on the test on the Wilson score adjustment. Yeah, so I'll explain that in a little bit. So sorry, I do have a couple more minutes of explanation to do. So let's do these. 95% confidence interval with 25 successes out of 281 trials. Same thing for here. And then we'll talk about why we can't use what we just learned to do this. Okay, so 95% confidence interval with x equals 25, n equals 281. So again, calculator wise, this is some easy stuff. Stat tests, one prop z interval, which is a. We had 25 out of 281. Confidence level 95%. Calculated up, there it is, 0.05568 to 0.12226. There you go. Let's do B. B was a 99% confidence interval for with 1,782 successes in 2,145 trials, so a much larger sample size. Calc tests, number A. We had 1,782 successes in 2,145 trials with a confidence level of 99% this time. There you go. There's your info. Not much to it. I'm really just asking the questions in the notes to get you to practice hitting the buttons on the calculator so that it becomes more natural to you. Yeah. So why can't we use what we just learned if we had 29 successes and 32 trials? Well, I'll let you think about that. I'll pause for a second. All right, I hope you paused the video and thought about that for a second yourself. But in general, whenever we can't do something, it's almost always because we didn't meet the requirements of whatever theorem we're using. So this theorem, central limit theorem for proportions, the one that tells us that the distribution is approximately normal, requires this. NP is the number of successes, NQ is the number of number of failures. And in our, where are we at here? In our question here, 29 successes in 32 trials, well, that's enough successes, but it's not enough failures. It's only 3 failures. So we didn't meet the requirements. And so we can't assume that the distribution is normal. And so we would have to do something else. We could still make a confidence interval here. We would just have to use a slightly different method, and I'm not going to worry about that. We do it by assuming that the sampling distribution is not normal, but is instead a binomial distribution. I'm not going to worry about doing that right now, though. Yeah, the basics are 29 successes and 32 trials is not enough failures. It's only 3 failures. Okay. Last thing, which is just extra credit on the test, a little nice to know. It is called the Wilson score adjustment. It's going to sound really random what he's doing here, what we do to do the Wilson score adjustment, but it's got some interesting and kind of deep math behind it. So here's the idea. So we don't know P, right? The confidence interval that we're making is attempting to estimate P, so we don't actually know it. So we can't actually calculate PQ over N. So instead we've been approximating it with P prime Q prime over N rather than PQ over N. And in general, we're gonna go ahead and keep doing that. However, one way you can account for this slight difference is the Wilson score adjustment. And the way Wilson does this adjustment is add 2 successes and 2 failures to the number of trials that you have. Like you're just making them up and putting them in. And you might say, well, that sounds utterly ridiculous. Why 2? It turns out that what that does is it essentially does a weighted average between 50% and your data. And that as your amount of data gets larger and larger, that just naturally heads towards just using the data. And I know that sounds like a very vague explanation, but that's essentially what you're doing when you do this. but it's literally just you add 2 successes and 2 failures, which is say 2 successes and 4 trials, right? X goes up by 2, N goes up by 4 because there's 4 imaginary trials that you're throwing in and 2 imaginary successes, and that's it. That's all you do. Your book doesn't call or so 2 things. One, your book doesn't usually use the Wilson score adjustment. It just does this for everything. And it also doesn't call it the Wilson score adjustment. It calls it the +4 method, which is a perfectly reasonable thing to call it, but you're cutting Wilson out of the deal, and that's not cool. So yeah, that's all it is. You increase X by 2 and N by 4, and it turns out that this actually gives you a slightly more accurate interval than not doing it. But in general, we're not going to worry about that. We're just going to continue doing this most of the time, unless we specifically ask for Wilson score interval. Okay, so practice with the Wilson score interval. I'm literally just going to add 2 to X and 4 to N and do exactly the same thing we did before. So here's Simone. She takes a sample of 28 regional managers, 7 of whom feel negative about the prospects for future business, 21 of whom feel positive. And so we're going to use a Wilson score adjustment to make a 99% confidence interval for the population proportion of regional managers who feel positive about the prospects for future business in their region. So 21 feel positive, 7 feel negative. I'm going to treat that as though 23 feel positive and 9 feel negative, which gives me a total sample size of 32. So we're going to do 23 out of 32. That's it. That's the Wilson score adjustment. Super easy. Stat tests, letter A. 23 out of 32. 99% confidence interval. Done. There it is. There's our estimate. Notice that this is a good example of a very imprecise confidence interval. Like Simone is 99% sure that somewhere between 51.4 and 92.3% of all regional managers feel positive about business in their about future prospects for business in their region. That is really wide. This is like just barely more than half, and this is just barely under all of them. So somewhere between essentially 50 and 100% feel positive about business in their region. It's not terribly useful information. She needs a bigger sample size. The sample size of 32, or actually 28, but our fake sample size of 32 is just not big enough, right? She just needs more people, right? Okay, so let's quickly go back to the notes, talk about everything we covered, and then wrap up this video. So remember this formula for confidence intervals. We will use this every time we make a confidence interval. Each of these pieces, the point estimate, the critical value, and the standard error, might be calculated a little bit differently depending on what type of data you've got and how much data you've got. But the basic formula always remains this. We learned 3 different kinds of confidence intervals. One where we know what sigma is, one where we don't know what sigma is, and then one for proportions. This one where we know what sigma is, very rare. It's not common that we end up using this. Almost always it's this one. For quantitative data. For qualitative data, it's just always this. Yeah, and that's kind of all I wanted to say about confidence intervals. And then again, you can use this sheet, by the way, on tests or anything that you're doing. Feel free. You can also just look up, if you just look up what's it called? T critical values. Like just Google T critical values, you'll get this chart. That's where I got it from. Yeah. So I think that's all I want to say about confidence intervals. Thank you for watching all the videos. I hope you enjoyed. And I will see you in the next one where we start talking about hypothesis testing, which is a big focus of the remainder of the course. So that is chapter 9. It's not till next week. You don't have to start learning that yet. The confidence intervals, I imagine, will take you the rest of the week. So good luck on the homework. I'll have a homework help video up soon enough. And yeah, I will see you in the next one.